If you don't understand what's going on and they're wondering, gosh, the person sitting next to me probably understands all this. They don't. Let's just next to Stephen. Okay. Axiom 2.
Right.
Axiom 2 is about unitary time evolution. And it is the statement that if the system is undisturbed by other systems, and undisturbed is a little complicated to define. Some would even argue this is a bit circular, but for our purposes, we'll say undisturbed means not engaged in mutual interactions, whatever that means, or exchange of information.
Almost, you might say, inertial.
Yeah, so if you begin to worry, this has ambiguity, isn't it, like inertial reference frames, excellent. But somehow we can imagine a system, it's just left to itself in some way. Okay, but of course, systems in an external, like electric or gravitational field, that's also allowed. So, but that's like quite isolated. Anyway, so you can run all these sorts of questions. But if you're not touching the system, you're not measuring, you're not disturbing it, you're keeping it pretty shielded from its environment, we say the system is undisturbed. If it's undisturbed, then there exists an operator, U, little hat for operators, we use hats for operators, that depends on t is the time, such that rho, the quantum state at any given time, is given by U times rho at the initial time 0 times U dagger. Okay? And this is not just any operator, this operator is unitary, which is a fancy way of saying that if you take this operator, give it as a matrix, and dagger it, you get the multiplicative inverse matrix. It's the multiplicative inverse matrix. So you give me the quantum state as represented by this thing. I should have given it a name. This thing, by the way, has a name. It's called the density operator. Quantum state in general is called the density operator of the system. You give me the density operator at the initial time 0, you wrap it up in U and U dagger, and out comes rho at t. And this is how you evolve the thing forward in time. It's called unitary evolution. Now, if the system has a rank 1 density matrix, its quantum state is rank 1, this simplifies. We only have to worry about the state vector or wave function. And we can think of the state vector or wave function. So if rho is rank 1, which literally just means you can factorize in this way, well, then the state vector exists. It is a function of time, and you can express it by taking the state vector at the initial time, multiplying it by this operator U, and it gives you the state vector at later times. So this thing that has a name, by the way. It's called the time evolution operator. Now, time evolution operator is a function of t. U hat is a function of the time t if it is strongly continuous, which is a bit of a term of art. Just think of it as smooth. I won't have to go the time to define what I mean by strongly continuous. But if it's like very smooth as a function of time, then we can take its derivative. Its derivative exists. We could imagine doing the derivative d by dt of u. And if we want, we can multiply it by u dagger. The resulting object has some properties that are made a little better if we multiply by the imaginary unit, and h bar is just good for units. This thing defines an operator called h. And this operator h by construction is self-adjoint. Its adjoint doesn't change it. The I is actually crucial for this. If you do the I inducement integration by parts, you'll find it the same. And this operator has a name. It's called the Hamiltonian. We say it is the generator of time evolution. And with the Hamiltonian in this equation, you could easily show that the state vector obeys a certain differential equation with a rather famous name and origin story. All you do is take a derivative. You do d dt multiplied by h bar of psi of t. You insert your formula u of t psi of 0 from our equation before, and you can show that this is equal to h hat times psi of t. And this differential equation, which you can think of as an infinitesimal differential version of unitary evolution, is called the Schrodinger equation. And some people have said this is like the dynamical law. It's like the F equals ma of quantum mechanics. Although, as we see, it's actually kind of a special case. You have to assume some things to get this particular equation out. It's not as general as you would have thought. That's axiom 2. Now, axioms 1 and 2 are sometimes called the Hilbert space axioms. And as you can see, they are just math at this point. I have said nothing about physics. I just said that there are these mathematical things, and the mathematical things have properties. The density matrix is positive semi-definite, unit trace, there's a state vector, there's the, you introduce a notion of time evolution, but what does that even mean? I'm just considering a sequence of quantum states represented either by density matrices or more simply when possible by state vectors. But what does this have to do with the real world, the physical world? Well, axioms 1 and 2 don't tell us that. They're just math. And so at this point, you might be wondering, gosh, I haven't seen any quantum mechanics before, or I saw quantum mechanics. This doesn't look anything like what I saw. Where's the particle in a well, and where's the eigenvalues and all that stuff? That's going to come in just a moment. If you're wondering, I don't really understand any of this. Maybe there's something wrong with my brain. The answer is no, your brain is fine. Well, it might not be fine. But not because of this. If this all seems very abstract, that's okay. If you don't understand what's going on and you're wondering, gosh, the person sitting next to me probably understands all this. They don't. Let's just do the answer, Stephen.